Hello, this is Dr. Liu. This question is a disc that has a rope wrapped around it. The end of the rope has a weight. So let's look at the numbers here. The disc has a radius of 0.075 meters. The rotational inertia is this amount. We don't necessarily know if the disc is a uniform disc or if it's actually a solid disc at all, but it's nice to have the inertia already given to us. And then there's the rope wrapped around its perimeter. So we know that the rope has basically this radius. And the other end of the rope is holding a 0.26 kilogram mass. The mass is held at 1.3 meters above the floor, and then you release the mass from rest. This causes the disc to spin and the mass to fall. So how fast is the mass as it is about to strike the ground? So let's create a diagram here. We're talking about a disc, right? So here's a disc, and we have a rope. So here's a mass that's held at 1.3 meters, and it's going to drop to this height. So let's do here 1.3. And this is not drawn to scale. Here's the radius r equals 0.075. And we also have a rotational inertia of the disc. Okay, 0.064. So, the mass here, let's put the mass here, 0.26. Everything is standard unit. So, since the question didn't ask any thing like the time it takes for the weight to fall this much, we don't really have to use torques. We can actually just use energy conservation. So if I just put a 1 here for snapshot of energy, the weight at rest, the disk is not spinning, so now we have no kinetic energy, just potential energy of this held up mass. And then as the mass falls down, it's going to spin the disk. So now we have both the mass and the disk with kinetic energy. The mass has translational kinetic energy, and the disk has rotational kinetic energy. But there's no potential energy left because the mass has reached the ground level. So we can use energy conservation. Let's do that. Let's write the generic term for mechanical energy. It includes kinetic energy of the system plus potential energy of the system. Kinetic energy is 1/2 mass. Let's see. Yeah, I think it's okay because there's only one thing with the mass. The disk only has rotational inertia. We don't know its mass. Good thing is not really moving the center mass. So this term is just the moving mass, and this other term is a spinning disk. And then we'll add the potential energy, just the mass, mgy. And because the rope is wrapped around the disk, there's no way for the rope to actually slip around the disk. So as the disk is spinning, the rope moves at the speed of the disk's edge. Right, the edge is moving at the same speed as the rope moving at the same speed as the falling mass. So we have this relation that V is equal to omega times R. This is where we actually use that radius in the expression. So we get omega equals V over R, and we replace that, and we have a value for I. So the total mechanical energy is 1/2 mv squared plus 1/2 I omega V squared over R squared, and then plus mg. We can factor out the V, and also 1/2 is a common factor, 1/2 V squared, and now we have m left, and we also have I over R squared left. So that is the combined translational and kinetic rotational kinetic energy, and then what's left is the potential energy. Okay, I think we're ready to plug in some numbers now. So for the snapshot at time 1, just potential energy. Alright, so this is just mgy1 126 9.8 1.3. So let's use our calculator, see if it's actually here. Oh, it'll take some time to load. Okay, so move it aside. So, oh, the point didn't come up. 126 times 9.8 times 1.3. So this gives us a total energy of 3.31 joules. Oops. Oh, what happened here? Okay, so 3.31 joules. And then we can calculate the other mechanical energy at the bottom. So maybe I should just draw this for the rope. So no more potential energy, just kinetic energy. So 1/2 v squared. We can put in the mass of 0.26 kilograms and the rotational inertia of 0.064. This is actually a pretty large rotational inertia. It requires quite a few kilograms of mass with an extent of almost 10 centimeters of radius. So it's a pretty heavy object. And then we divide by 0.075 squared. So this is v squared. There's a 1/2. There's all these. So let's calculate them in Python. So we'll do 0.26 plus 0.064 divided by 0.075 squared. Okay, so 11.63. And then we can multiply by 1/2. So we have 5.82 as a factor. So v squared times 5.82. And now we can equate the two energies. E1 equals E2. So 3.31 joules. Let's skip the unit. The other side didn't have a unit either. Is equal to 5.82 v squared. So we have v squared is equal to 3 over 5, and we can take a square root. Okay, let's use Python again. We have parentheses here, so 331 over 582. Take the square root. So we have velocity is 0.754. meters per second. Okay. So this question is different from just a simple mass falling down using energy conservations, because there's this big big disk that has mass and rotational inertia. So as long as you count it in, here's how to count it in: 1/2 inertia times speed squared. That's angular speed. As long as you count it in, you can use the same ideas of energy conservation to find out the final speed. And here's this one right here. We call this non-slip condition. I'm pretty sure if you wrap rope around it, there wouldn't be any slipping. Maybe toward the end, when the end of the rope, if you didn't secure that to a peg, or maybe didn't nail it down, that would slip. But this is what happens before that ever is happening. So the rope moves at the same speed as the mast, and the rim of the disc moves at the same speed as the rope. So we can establish this relationship to get rid of the angular velocity, and now we're only left with linear velocity, which is what we're used to. Okay, thank you.